Managed Aquifer Recharge, Water Security and Sustainability in Our Changing Climate, presented by Monique Gastolden. On Earth, our blue planet, groundwater provides the second largest source of fresh water and as such is depended upon around the world as a reliable source for consumption, agriculture, industry, mining and for the environment. Globally, groundwater fulfills demands for nearly 2 billion people and provides more than 40% of water consumed for irrigation. However, globally, our groundwater supplies are diminishing. The United Nations states that over 1.7 billion people are currently living in river basins where water use exceeds recharge, and water scarcity now affects more than 40% of the global population, with this figure set to rise due to climate change and population growth. These stresses on our world's aquifers are casting doubt on the future ability of groundwater to meet water demands. Therefore, the utilisation of more diverse methods for securing water supply into the future are needed. Managed Aquifer Recharge, or MAR, is the intentional recharge of water into aquifers for storage and subsequent recovery or environmental benefit. This innovative option uses water that may otherwise be wasted and can help buffer the effects of climate dependence of water and may provide a secure and sustainable supply into the future. Water security is a grave concern in countries like Australia, where we are experiencing rapid population growth and a drying climate. The Australian Bureau of Statistics predicts the four biggest cities, Sydney, Melbourne, Perth and Brisbane, will increase their population by 46% by 2031. That's an estimate of an extra 5.9 million people. Predictions based on the fifth climate model of the Intercomparison Project of Global Climate Models, or the CMIP5, forecast with high to very high confidence that in the major cities across Australia there will be increases in temperatures and evapotranspiration, more extreme heat days, an overall reduction in rainfall, but with higher intensity rainfall events. This can result in more stormwater becoming runoff and causing flooding and even less recharge of groundwater due to soil saturation. The use of managed aquifer recharge within urban catchments can help cities cope with this runoff variability exacerbated by climate change in order to bank water for long-term storage and future use. In addition, by storing water underground, MAR can decrease water loss via evaporation, eliminate above-ground storage issues such as algal blooms and mosquitoes, and presents a smaller land footprint compared to surface water storage, which is particularly relevant in urban areas where the value of land may be high. MAR also has the potential to make better use of previously unutilised water sources such as recycled effluent and can also address the problem of seawater intrusion into coastal aquifers. In addition, it can offer other co-benefits for the environment, including contributing to environmental flows and supporting groundwater-dependent ecosystems and adding value and amenity to urban locales. With growing freshwater scarcity, we need to close the water cycle gap. MAR seems to be a key tool that can be utilised in integrated water management strategies and as an adaptation to climate change. But there are a variety of MAR processes that may be adopted, which utilise different source waters and help serve different purposes. A variety of source water can be used in the recharge process, including stormwater, rainwater, surface waters, desalinated water, treated effluent, and even mains water. It is important to understand the quality of the source water to determine the best MAR process to use. MAR relies upon the natural treatment processes within aquifers, such as filtration, sorption, and redox transformation, including biological nitrification and denitrification, and degradation to polish the source water. Recharge water that is close to drinking water quality is best utilised for direct or indirect injection, whereas more degraded water quality should go through infiltration methods, which enhance the natural processing that occurs within the aquifer. Of course, differing end uses of the water with different associated guideline values must be considered when looking at post-treatment. For example, water used for irrigation of crops or green space or non-potable urban or industrial use may require less intense processing than water for potable reuse. There are a number of methods used to recharge aquifers. Types of MAR which use well injection techniques are generally suited for deeper confined aquifers and include ASR, or aquifer storage and recovery, which retrieves water from the same well and is useful where storage is the primary goal and water treatment may be of less importance, or ASTR, aquifer storage transfer and recovery, where recovery is from a different well and is useful if a longer residence time is required within the aquifer for the natural processes to occur. However, a MAR project may only be feasible if its recharge water is located near the injection site and can ensure a steady supply. Types of MAR which utilise infiltration structures such as ponds, basins, galleries and trenches allow water quality to be enhanced prior to reuse. MAR and other traditional urban water storages are not mutually exclusive. In fact, surface waters can provide detention time to allow for groundwater recharge. A regional network of distributed stormwater collection managed aquifer recharge projects could increase groundwater supplies while contributing to improved groundwater quality and flood mitigation. The type of MAR configuration and the engineered treatment requirements vary considerably depending on the ultimate purpose of the recovered water. In an urban setting, impervious cover alters the natural recharge regime of groundwater and urban stormwater runoff. Stormwater, although usually in plentiful supply, indeed in many urban centres the volume of stormwater runoff is greater than its entire combined household water use. It is, however, seasonal in nature. Therefore, MAR can provide a storage and treatment option in preparation for subsequent use in periods of high demand, for example during dry spells. However, stormwater can be a major source of pollution in urban catchments, carrying with it heavy metals, hydrocarbons, organic compounds, nutrients, micropollutants such as herbicides, pathogens, and other contaminants of concern. Traditional urban drainage systems may contribute to this mobilisation of pollutants. Therefore, it is imperative when adopting MAR processes that green infrastructure and water-sensitive urban design strategies are incorporated in order to help manage water quality. MAR can be used in combination with other sustainable urban water management approaches such as wastewater recycling, stormwater harvesting, saline groundwater intrusion, and flood management and mitigation. Importantly, MAR has a vital supporting role in achieving the objectives for water-sensitive urban design, integrated water cycle management, best management practices, sustainable drainage systems, low-impact development, and green infrastructure by providing the large volume storage capacity for water in urban areas. Under triple bottom line evaluations, the environmentally friendly aspects of MAR are advantageous in relation to coastal water quality, greenhouse gas emissions, aquifer restoration, and urban amenity. However, MAR requires the management of both water quantity and quality to ensure protection of public health and the environment, while developing a water resource for beneficial use. Aquifers can polish or ameliorate the quality of the recharge water through natural processes, and several studies have looked at the degradation and absorption of organic micropollutants in MAR systems. Aquifers harbour diverse microbial communities which can facilitate the natural attenuation of nutrients through microbial metabolic processes. MAR operations will passively remove organic carbon and nitrogen, but the removal of nutrients is highly variable and site-specific, with increased residence time having the most beneficial impact on water quality. For example, at Fluorite Infiltration Gallery site near Perth, Western Australia, changes were tracked over a 39-month period, with reductions of phosphorus at 30% and total organic carbon at 51%. However, other conditions also affect the processes. One example of a noxic brackish limestone aquifer for wastewater demonstrated 46 to 87% removal of total nitrogen, but virtually no impact on the phosphorus. While another study by Ying et al. In 2008 found that in aerobic aquifers, in the presence of nutrients, several endocrine disrupting chemicals were biodegraded. However, this was not the case in anaerobic aquifers. Clay minerals, iron and manganese hydroxides and microorganisms present in different aquifer zones have the capacity to decontaminate and fix metallic pollutants and metalloids. But when groundwater has long residence time in an aquifer, it can lead to dissolution of the aquifer matrix, such as calcite and dolomite, particularly if it receives large influxes of surface water with a different composition. The resulting geochemical reaction can mobilize metals such as arsenic, iron, and manganese, and could potentially lead to structural instability of the injection wells over the long term. Choosing a MAR site, therefore, requires that the quality of the recharge water is compatible with the soil's reactive processes, especially in the unsaturated zone. However, it is the emerging contaminants, often engineered and manufactured by humans, including pharmaceuticals, nanoparticles, microplastics, pesticides and herbicides, and PFAS, per and polyfluoroalkyl substances, that are proving to be a significant challenge for integrated water management and may ultimately influence the viability of water recycling via aquifers in the future. The group of chemicals known as PFAS have been used broadly by industry in a range of products for its properties as a fire retardant, stain preventer, water repellent, and non-stick covering. PFAS are water-soluble with very stable carbon-fluorine bonds, meaning they are highly resistant to biodegradation and photodegradation, and can be transported long distances in waters, with urban runoff and wastewater being a significant carrier. PFAS plumes extending for hundreds of kilometres from source areas have been observed in some locations, for example Oakey and Williamstown, which indicate that PFAS compounds can be highly mobile in some groundwater aquifers. Although PFAS transformations via oxidation processes and microbial activity may be possible in the aquifer, the result could either be a decrease or an increase in PFAS concentrations, as suggested by studies on stormwater processes and wastewater treatment plants. Increases in concentrations are presumably due to PFAS transformations via processing into its precursor compounds. Attenuation of PFAS via adsorption still remains the most reliable method due to the physiochemical properties of PFAS, but is highly dependent on the hydrogeological site-specific conditions of the Mars system, such as aquifer type, temperature, redox state, and mineralogy. Granular activated carbon, or GAC, has been used successfully to ameliorate PFAS in water, but other technologies such as ion exchange resins, sonochemical treatment also appear promising, with reverse osmosis providing the most significant log reductions of PFAS in trials to date. Engineered pretreatments which may be adopted are often already used in Mars systems to remove turbidity or nutrients and reduce the risk of clogging during recharge. Clogging can be one of the major operational issues for Mars recharge systems and in the integration with sustainable urban water management. The issue is less of a concern in surface infiltration systems such as SAT. Clogging develops over time as a result of the interaction between the source water, the native groundwater, and the porous media. Reactive minerals in aquifers such as carbonate can help to control clogging through dissolution, but as mentioned previously, this can also affect the quality of the recovered water through the mobilization of metals. Stormwater as a source for Mars can be problematic as it can lead to chemical clogging, mostly associated with iron oxyhydride precipitation. Other causes of clogging include biological and mechanical clogging. However, it is physical clogging via suspended solids, fines migration, fracturing of the aquifer, and damage that occurs during bore construction, which is the most common cause, with one study by Du et al. In 2018 identifying it as the culprit in 70% of clogging cases. Although heterogeneous soil characteristics could significantly reduce the risk of clogging, increasing treatments prior to recharge, such as sand filtration or UV disinfection, can reduce total suspended solids, increase infiltration, and reduce the risk of clogging. There are many potential combinations of water sources, water treatment methods, and recovered water end uses of Mars. The degree of pre-treatment will usually be driven by the source water and aquifer type, while the post-treatment will be driven by the end use. The oldest successful example of Mars in Australia is in the Burdekin Delta near Townsville, Queensland, where strategically located recharge pits allow diverted river water to percolate through coarse sands for aquifer recharge. Individual pits can recharge as much as 20 megalitres per day, with up to 45 gigalitres a year stored underground, which is predominantly used for sugarcane irrigation, but has the added benefit of minimising the threat of seawater intrusion. This scheme was only achieved through a unique collaborative approach between water managers, government agencies, research bodies, natural resource groups, not-for-profit groups, and industry. In 2006, the Burdekin Water Futures Group was formed to facilitate a more strategic approach to water management in the Burdekin, with the mission being to support a long-term strategic, whole-of-system approach to understanding and managing the lower Burdekin water resources and associated systems, and thereby deliver long-term economic, social, and environmental outcomes that ensures the region's sustainability. In Australia, there have been other successful Mars schemes, including in the Northern Territory, where Australia's first soil aquifer treatment scheme stores treated wastewater underground and augments groundwater resources in Alice Springs, and a scheme which stores shallow groundwater in a deeper aquifer to supplement the drinking water supply on Goulburn Island. Adelaide has a number of schemes which inject stormwater into deep limestone aquifers for non-potable use, such as irrigating public spaces. Currently, the South Australian State Government are jointly funding with the Federal Government the Northern Adelaide Irrigation Scheme, which will see new water treatment facilities built within the Bolivar precinct that will treat, store and transport climate and season-independent water for agri-food production. Australia's first full-scale groundwater replenishment scheme is located in Perth's northern suburbs in Craigie, Western Australia. It started recharging recycled water to Perth's deep aquifers in 2017. The advanced water recycling plant takes the wastewater through a number of treatment processes to make it suitable for recharge, and it will, at capacity, recharge 2 large aquifers on site, with the remaining volume of water being transferred to recharge bores further away. The success of the groundwater replenishment scheme in Perth was in no small part due to the extensive community engagement program they embarked upon in 2004, 5 years prior to the commissioning of the treatment plant in 2009. The communications focused on two main groups, the regulators and opinion leaders. Conducting a trial was also a key factor of success, and much support was gained via education, with a visitor centre offering tours, which helped to overcome the yuck factor within the community, resulting in 76% support of the groundwater replenishment scheme at the end of the trial. Regular stakeholder interactions with government, including elected members, key health and environment organisations, industry and key community groups, were conducted throughout the 3-year trial. By the end of this trial, after significant testing, approval was granted by all 3 relevant government agencies, with the regulatory framework, the Wastewater Quality Framework, in place, which was based on the 12 elements of the Australian Drinking Water Guidelines and the Australian Guidelines for Recycled Water. Water utilities, whether they be government entities or affiliated with governments, have a core business which aligns with Sustainable Development Goal 6, ensuring availability and sustainable management of water and sanitation for all. This is not just for today, but for tomorrow, next year, next decade, and for the next generation. Where a single urban entity is responsible for municipal water, sewerage, and stormwater, such as in a local government water utility, sustainable management of these 3 resources can be more easily implemented. Therefore, it is these water utilities who are best placed to deliver and manage MAR schemes within the broader context of integrated water management to provide a sustainable and safe water supply that is more resilient to the impacts of climate change and increasing populations. But the success of these schemes is dependent upon collaboration and communication with other stakeholders and the community. It is critical to build trust between MAR operators, regulators, and the larger community for MAR systems to be sustainable and well accepted. Environmental and human health regulators should be involved from the outset in planning and delivering communication and engagement activities. Resources need to be directed into identifying and researching appropriate sites for MAR schemes for the future. And now that we are armed with several decades of research, we can better understand the combinations of source water types, aquifer, and MAR operational conditions that lead to specific changes in water quality and plan with those parameters in mind.